to introduce you, but the rule is that you finish when you finish.
Oh, okay.
I don't stop. Except at some point, everybody will.
I would hope to stay 2 hours. Everyone wants lunch.
Maybe if it's 1 hour and a half or 55 minutes. No. Donc, le deuxième exposé ce matin est fait par Lillian qui parle de la méthode de la valeur moyenne de Vinogradov.
Thank you very much. I will speak about the Vinogradov mean value theorem, which pertains to exponential sums. And this will be presenting the work of Wooley and separately Bourgain, Demeter, and Guth. Now today, the treatment will break into a few parts. I'll present just a couple motivations out of many. I'll state what has become known as the main conjecture in this area, which is now a theorem with 2 approaches to it, one of them which has reached the complete proof of the main conjecture in all cases. I will then speak about a notion of decoupling, which is the name of one of the new methods, to make it more familiar. And I'll end with a few basic elements involved in the proof of the main conjecture, treated in a simple exemplar case, which allows us to see both of these methods in action simultaneously. So, to set the stage for why Vinogradov came up with this conjecture, I'll mention only 2 motivations, very briefly. One of them has to do with Diophantine equations, in particular Waring's problem. So, originally posed in some form in 1770, but I'll be referring to the setting that Hardy and Littlewood took up in the 1920s, which says if Rsk of n is equal to the number of solutions to the diagonal equation x1 to the k up to xs to the k equals n, then Hardy and Littlewood's goal was to show that for the number of variables as small as possible, denoted traditionally by capital G tilde of k, this is as small as possible, there exists some delta, depending on s and k, such that for all n sufficiently large, in a sense completely determined by s and k, we have an asymptotic for this expression with something called the singular series, which is an arithmetic quantity I will not speak about today. There's the main term you should pay attention to, and there's a smaller error term, which saves by this delta. And so the goal is to show that this can be proved for s as small as possible. How does an exponential sum come in? Exponential sum. Well, this has to do with a Fourier expansion. So you can represent this as an integral from 0 to 1. You sum x up to capital N to the 1 over k, and you take e of alpha x to the k. You raise that sum to the s power if you're looking at s variables, and you integrate against e to the minus n alpha, and this represents this counting function by orthogonality. I'll be using the notation that e of t is e to the 2 pi I t. So Hardy and Littlewood's circle method, as depicted here, says that for alpha very close to certain points, so for example 0 or rational numbers with small denominator, this sum is actually genuinely large. And in a small neighborhood, you get a term which contributes something of this size. And the goal is to show that away from these neighborhoods, this sum is rather small and only fits into the error term. In particular, if you want to be able to treat fewer variables, you need to be able to give good upper bounds for exponential sums of this kind. And this was one of Vinogradov's motivations. The other motivation I will very briefly mention is the Riemann zeta function. So the idea there was that for s equals sigma plus it, sigma close to the 1 line, there's an approximation of the zeta function as a finite sum. And if you want to show there's some zero-free region, you would be interested in doing so if you want to try to prove the Riemann hypothesis, for example, or just count primes a little bit more accurately. You'd be concerned with Dirichlet sums in some region. Now, in fact, by partial summation, you can look only at the oscillating part. And this does not yet look like an exponential sum, but you can rewrite it in this fashion, and then Taylor expand, and you arrive at an exponential sum of some polynomial. So again, you want to be able to control such sums. So what Vinogradov brought in a 1935 paper was a mean value perspective. So he studied the following sums. So this is the sum from little x up to big X of e of alpha 1x up to alpha k x to the k. So alpha lives in the unit square. And he also defined jsk of x to be the mean value of this in the moment sense. So raised to the 2s moment and integrated over alpha. Here, we're going to think of s and k as being integers for the moment. Now, in the case that s is an integer, so 2s is an even integer, you can use orthogonality to expand this and turn it into a counting problem. So you can rewrite this as the number of solutions, these are 2s variables, to a system of equations. First, you have a linear equation. Then you have a quadratic equation, all the way down to a diagonal kth power equation. All right. I'll be speaking of this, loosely speaking, as a Vinogradov system, or the Vinogradov system. If I say that again, you'll know that it means the system of k equations. All right. So, of course, it's critical that Vinogradov knew that from such a mean value, you can extract a bound for one Weil sum. And what his goal was to show that there were good upper bounds for this mean value, Js of k. To get a grip on its size, it's helpful to look at the easier question of lower bounds. So first of all, we can see that the diagonal solutions, namely when the first s variables are equal to the last s variables as sets, this tells us that trivially we have at least the order of x to the s solutions. On the other hand, what about solutions from alpha near the origin? So for example, for each j up to k, you could look at, say, those values of alpha that are proportionately close to the origin based on a certain well-chosen power of x. Now what this tells you, if you look not at counting integral points, but at the integral itself, you'll find swiftly that this is bounded below, first of all, by a power x to the 2s, because for alpha so close to the origin, the sum is trivially large. And then we have the measure of that set, which is 1/2 k plus 1. So these are two lower bounds. Now the main conjecture, as Wooley has dubbed it, is that in fact these lower bounds represent upper bounds as well. So for all integers s k greater than 1, for every epsilon greater than 0, for all x greater than or equal to 1, the conjecture is that jsk of x is bounded above by some constant depending on sk and epsilon times x to the epsilon times x to the s plus x to the 2s minus 1/2 k plus 1. And a note on notation, instead of specifying constants, I will typically use Vinogradov's notation, less than, with some specification on the dependence on various parameters. All right. Now let's just briefly understand how this conjecture would impact Waring's problem. So in the time of, say, Weil, who had pointwise upper bounds for exponential sums that Hardy and Littlewood used, Hardy and Littlewood were able to show that the number of variables required in Waring's problem was exponential in k, roughly 2 to the k. If you have the main conjecture, then it is possible to show that this is quadratic in k with various improvements, but the main term is about k squared. Now conjecturally, g tilde of k is linear in k, so it sounds like I'm bursting the bubble of the power of the main conjecture. The point is people are extremely happy that Waring's problem has had the number of variables reduced as low as k squared, even if we eventually hope it will be as low as 2k plus 1, and some people hope k plus 1. What about the Riemann zeta function? So Vinogradov's work did not prove the main conjecture. I'll tell you in a minute what it did prove, but it did result in what is today still, in terms of its overall shape, the best known zero free region called the Vinogradov-Korbakov zero free region. Unfortunately, one of the few things that these terrific new methods have not been able to improve is this zero free region. And that comes about because of the dependence of this constant. So if you're Taylor expanding this log up here, you're going to be able to truncate it at various powers, and you're going to need to know how this constant depends on where you truncate it. And the methods of proof for the main conjecture right now don't tell us that information. So this remains the best known, but there have been dramatic improvements to Waring's problem and many other arithmetic problems based on the main conjecture. Okay, so this conjecture has been around for a long time, 80 years. So I will not summarize all of the history, but I will just give you a few key points. So first of all, there are two cases that are genuinely trivial to show, k equals 1 and 2. And And in fact, in the expose, I go ahead and prove these explicitly. We'll see heuristically a little bit about the case k equals 2 later. Now, interestingly, it's not that the cases gradually become harder. In fact, the case k equals 3 is already highly non-trivial and was not resolved until a couple of years ago. Now, importantly, for each k, if the main conjecture is known, just for one value of s, the value of s where the two terms are of the same order, so this is always going to be denoted s sub k, and I'll call it the critical index. So if the main conjecture is known just for this one value of s, it follows for all s. And just to emphasize, for that k only. And this treatment is also not so hard, and I give it in the expose. Now, this critical index naturally reduces work into two different cases. Do you try to approach the critical index from below or from above? So for small s, there were a few easy cases. So if you're looking at very small s, you can use the Newton-Girard polynomial identities. This doesn't take you very far. We have to get all the way up to quadratic in k. Even just one more case was quite difficult. This was due to Vous. I'll jump now to large s, which has been the historical focus. So in the Vinogradov era, which I will take to include work of Linnick in the 40s, Karatsuba in the 70s, and Stechkin also in the 70s, the consequence was that the main conjecture is known for all k greater than or equal to 1, as long as s is at least 2 times k squared log k plus O of log k. So this is off from the critical index, first of all, by the factor 2, but more importantly by this logarithm. And it was big news that in Trevor Wooley's thesis in the 90s, that he was able to improve this to 1 times k squared log k plus O log k. And this was by a method he called efficient differencing. Now, the new work that I am here to speak about today comes in two flavors. So there's work of Wooley by a method he has called efficient congruency. And this started in about 2010. The first published paper is 2012, but the ideas were there earlier. And there are at least 11 papers having to do with improvements and consequences of his method by Trevor Wooley. So his first breakthrough annals paper was that the main conjecture holds for all k greater than or equal to 1. The key part is assume as s is bigger than or equal to k, k plus 1. So this is an improvement in the sense that it gets rid of this log, and it was the first result to do so. I will jump to the state of his work by December 2015. So at this point, he had proved that the main conjecture is true for k equals 3 and all s. So he was the first person to resolve the main conjecture for a degree higher than these trivial degrees in full for all s. for higher degrees, he had resolved it for s greater than or equal to k times k minus 1. And remember I said you could try to get to the critical index either from above or below. He actually got very close from below. So he had the correct leading term, which was a real tour de force, and it was off only by a lower order term. So this was the state of affairs there. And then in December of 2015, there was a preprint on the archive, which was very stunning, that approached this from what seemed like a very different method called L2 decoupling. This fits in with a school of, at the moment, about 20 papers. I'll come back very briefly to who's involved here, but there's only one by these three, but it's in a tightly knit school of papers involving many by Bourgain and or Demeter. All right, so what did they prove? They proved that the main conjecture holds for all k, all the remaining cases. And in fact, their proof applies to the lower cases as well, but the new part was degree 4 and higher. I'll just make a note here. I stated the main conjecture as an upper bound, but it's well known via circle method techniques that once you have an upper bound, you can deduce an asymptotic for appropriate parameters. So as a consequence, it's now known that an asymptotic holds of the form that is asymptotic to some constant. This is actually a singular series and a singular integral times x to the 2s minus 1/2 k plus 1, as long as s is strictly bigger than the critical exponent. This is in the case 3 and higher. In fact, there is an epsilon necessary in the quadratic case. Okay. Now, analytic number theorists are no stranger to Fourier analysis, but in fact, decoupling seemed to come from a somewhat different neighborhood than number theorists usually use. So I want to pause and give a notion of decoupling before I even state the theorem that Bourgain, Demeter, Guth actually proved, which resulted in this consequence. So it helps to remember, first of all, a notion of orthogonality. Let's just say, for starters, in L2 of the unit interval, so we have an inner product that's just f integrated against g bar. So if you have a set of pairwise orthogonal functions in this space, then if you're interested in the L2 norm of some finite sum of them, well, you can rewrite this as an integral like so. And then using the pairwise orthogonality, you see that the only terms that remain are when you choose j to be j prime. So you can rewrite this actually in two ways. You can either write it as a little L2 norm of big L2 norms, or it turns out to be the same to write this as a big L2 norm of little L2 norms. And in fact, this argument still works if, sorry, they should all be f sub j's. If each f sub j isn't orthogonal to all the other ones, but is, say, orthogonal to all but 2 of the other ones, or all but I to the epsilon of the other ones. But let's just say here is orthogonal to all but 2 others, just to be precise. We just end up with a constant square root of 2 that would float around on the other side, and then an upper bound. Okay. Now, what if we did not assume anything about orthogonality? Well, then pretty much the only thing we could likely think of doing is to use the Makowsky inequality. It's a little bit hard to compare this to these sums up here. So let's use Cauchy-Schwarz, and we get back something more comparable. And we see that we lose, if we don't have orthogonality, by this cardinality of our set to the 1/2. This is why some people would say this has square root cancellation, and this does not. All right, so obviously we'd rather not lose by such a big factor. So there are 2 questions you could ask right away. Well, where do I get orthogonality? Another question is, this was all well and good for big L2, but what about other LP spaces? Can I recover something of this nice behavior? So, just as one observation, say we're on L2 of Rn, we have Plancherel's theorem. So we learn from this that the inner product of f and g is equal to the inner product of the Fourier transforms. So one way to get orthogonality is disjoint supports of the Fourier transforms gives us orthogonality. Now that's not the only way, but it's one very nice way. And this is the motivation for Littlewood-Paley theory. Now just to have a very simple example, let's stick to the real line. So the idea here is that if, say, you're initially given some L2 function, we're going to write it as a sum, an infinite sum of functions, fj, where we define fj by taking the Fourier transform of f and truncating it, this is a characteristic function, to the place where sig c lies inside an annulus. Okay? Then each of these fj's has disjoint Fourier support, and so the fj's are orthogonal. And so we get this beautiful relation that we had over here. But the point of Littlewood-Paley theory is that we also get something quite a bit more, which is that if we look at the little L2 norm, in LP norm now, not just L2, that this is bounded above by some constant times the LP norm of f. Say f is in LP, so that's finite. And in fact, it's bounded below also. And this is for p between 1 and infinity. Now, why did I mention this? We need to get back to arithmetic sooner or later. The point is that this is called a square function. And this here is called a square function estimate. And crucially, it has the little L2 norm inside and the big LP norm outside. Now, there are many other questions this leads to, so things get very complicated on higher dimensions. So in general, you can ask, how else can I decompose f hat? Also, can I decompose it by restricting it to curved submanifolds, for example? This leads to ideas from restriction theory, which are very tightly interwoven with decoupling, which we're going to get to now. Let's see. So I'm going to define the notion of decoupling a bit informally at first. So we will say that a set of functions satisfies little L2 decoupling on big LP if, for our set of LP functions, we have the claim that for all epsilon, if we look at the sum for indices in some finite set in LP norm, then this is bounded above up to a small loss by the set of LP norms taken in little L2. All right, so this is for p not equal to 2, this is a reversal of the square function. The little LP norm is inside now, and we're losing by some small factor. But let's suppose an estimate of this type holds. So it almost has square root cancellation. So it looks like these functions are almost orthogonal in some sense. What else can we observe? It's weaker than the square function estimate if p is strictly bigger than 2. So you can show that if you reverse and put the LP norm outside, that's always a smaller quantity than having the LP norm inside by Makowsky's inequality. And this computation is done in the expose. And it's not in general expected to hold if p is strictly less than 2 or p is equal to infinity. So in general, you'd hope that if you have a set of functions that are at least orthogonal on L2, that you would be able to show a decoupling estimate up to some critical exponent somewhat bigger than 2. So this is, in an informal sense, the general notion of a decoupling estimate and what range you would expect, if you're lucky, to be able to prove something. Now, who was involved in this development? So there was a paper of Wolf, which actually originated a notion of, in his case, little LP decoupling for big LP. This was then taken up after his death by Labat, Pramanik, and Ziegler in various combinations of those authors. So in the early aughts, they had some papers on what were then called local smoothing estimates. And then Bourgain reintroduced this study. And Bourgain and Demeter then were the ones to obtain a breakthrough, and they proved sharp L2 decoupling for paraboloids and other surfaces. But what we're going to focus on is Bourgain, Demeter, Guth, which builds on all of these methods to prove a certain theorem that I'm going to state in a moment. Now, we need to ask, however, how does Vinogradov fit into all of this? So I claim that the main conjecture can be written as a decoupling estimate in the following form. So we're going to look at a finite exponential sum. And I'm going to take an LP norm, specifically that choice of p. on the space, the K torus. And we're going to suppose that we've proved something of the following shape. So what would a decoupling estimate have? Well, it would have the LP norm of each of these functions, right? We're thinking of this as being our f sub j. Well, the LP norm of an exponential is very boring. It's just 1. That's going to be OK, it turns out. All right, here we are. So this is 1. So this sum on the right-hand side is x to the 1/2 plus epsilon. This doesn't look so good yet. But let's take k plus 1 powers of both sides. So if we take the k plus 1 power of both sides, what would we get? Well, we'd get a particular instance of JSK on the left-hand side, and we'd show that it's bounded above by 1/2 k plus 1 plus epsilon, some other epsilon. And that's the main conjecture. This is the main conjecture at the critical index. And remember, I said that if you can prove it at the critical index, you're done for all s. So does everyone agree we can express the main conjecture as a decoupling estimate in this rather trivial looking way? Okay. So in fact, this fits into a larger paradigm of a sort of discrete restriction type estimate. So this is an idea that's been around since the 90s, worked on heavily by Bourgain. So let me just generalize it slightly. What if we had some arbitrary complex coefficients? We sampled not at integer points, but just at some one-separated points. We took some LP norm, not necessarily this particular one. We'd want to bound it above by the little L2 norm of these complex points. And we'd want to do this uniformly in the sequence AJ, these are just complex numbers, and TJ, which we'll say are one-separated. What I mean by that is that they can't cluster together. They're forced to live in separate unit intervals. So at most, 2 of them can be very close together. So this paradigm itself can be thought of as a discretization of a continuous integral. So what if we integrate from 0 to 1 some nice integrable function along the curve, which is called the moment curve. So we'll say gamma. I'll say sub-0, 1 because we're only looking at this compact portion of it. This is the curve t squared up to t to the k, with t between 0 and 1. And this lives inside Rk. OK, so it's fairly reasonable that we can think of this sum as a discretization of that. So what's going on? If we look at the case of the parabola, what we're saying is that we sampled it, here's the point 1, at some points. Now technically I said tj are separated by integers, but here let's say that in fact we're sampling at points we've normalized by big X, and then they all lie between 0 and 1. Now what is this object? This is the inverse Fourier transform of the function g along the moment curve. And you could see this. If you assume that, in fact, g acted on k variables, but you had some delta functions that restricted you to the moment curve, you would get precisely this integral back. As such, it's called an extension operator. So the origins of that come from restriction theory, which is a motivation underlying a lot of this. So this is an extension operator. The idea is you started out with something that lived only on a curve, and you got back a function that lives on k variables. So finally, I can state the theorem. Let's see where I am. I think I want this guy. So here's the theorem that Bourgain, Demeter, and Guth proved. We can say it's sharp L2 decoupling for the moment curve. So it goes as follows. Fix k an integer greater than or equal to 1. For every epsilon greater than 0, for every delta at most 1, and for every ball B in RK of radius delta to the minus k, so that's very big because delta is small. For every integrable function g, we have the following decoupling estimate. So we take the extension operator of g, we evaluate the LP norm for a particular choice of p. Now what is this? We could have written this. Here we have our curve. We could chop this up into little pieces, little intervals j, say with length delta. We could partition it in this way. And then we could define an extension operator that doesn't integrate from 0 to 1. It only integrates over that little piece j. And we'll call that E sub j. So we could write our extension operator as a sum of pieces. This is setting us up for decoupling. Now, the number of such pieces is delta to the minus 1. So we get a delta to the minus epsilon as our small loss. And then we have a sum over this partition of these LP norms. And in the decoupling style, we have the little L2 norm of them. So this should look like a decoupling inequality. One thing I haven't defined is what does this mean? This is an LP norm smoothly concentrated on the ball B. And I won't really define what that means, but it just means that it's, you can think of it as being sharply truncated and only integrating over the ball B, but in fact it does so smoothly with small tails outside of the ball. So I won't show you exactly how to deduce this discrete version from this theorem, but that is a pretty simple deduction, and the main difficulty is proving this decoupling theorem. Now, in what sense is it sharp? It's sharp in the sense that it does not hold in general, if p is strictly bigger than this exponent, nor need it hold in general for smaller balls B. So in that sense, this estimate is sharp. If they had not achieved this particular choice of P, you could not deduce the main conjecture. That's what allows you to prove the main conjecture in the critical index case. Now, what are some key elements in the proof? So it's a very technical proof. And this is, of course, leaving things out. But here are three main philosophies. First of all, you want to work at many scales, meaning that you want to partition into smaller and smaller pieces through some iterative means, and consider all of those scales at the same time. Number two, it's crucial to have a multilinear perspective. And I'll come back to exactly what that means. The third thing is some notion of transversality of various components. And I will come back to what that means. Now, the nice thing is that, in fact, these three key elements for the proof of decoupling also arise in Wooley's work in disguised form in the efficient congruencing method. So what I'm going to close with is a very simple exemplar sketch of a few of these elements in parallel between these two arguments. And we're going to look at the very simple case of the moment curve, and we're going to try to bound JSK in this case. Now, I should say this is known by an elementary argument, but it's a good testing ground. Okay. So to keep things very concrete, we have the critical exponent is 3. So we're counting solutions to a set of two equations. One of them linear, one of them quadratic. And we want to count how many solutions up to size x there are. Well, there's a heuristic. It's certainly not a proof, but let's just do it for the moment. So we could solve for one variable in the linear equation and pretend we only have 5 variables left to choose. Now, once we've chosen these 3 over here, we have a sum of squares equals a fixed integer, and we'd expect at most divisor of n values for that. So it's reasonable to conjecture and not too hard to actually prove x to the 3 is what you want to show. Now, although I gave you the proper decoupling theorem, we're going to keep things very concrete and just talk about finite exponential sums. So we're going to define a function which is just the sum over the integers in some interval I, tx1 plus t squared x2. So this is our Weil sum of interest. And we're also going to define a quantity that is the same sum, except we restrict T to lie in some residue class mod B to the A. Now, what is P? I haven't told you, but I will. And it's fixed, so we don't denote it in the notation. So these are going to be our 2 objects of interest. So we're ignoring this continuous version I just told you about and talking about this discrete version. So what's our goal? Well, it would be to show that if we look at the LP norm of this, that we get, oh, that's a different P, isn't it? I'm sorry, they look very different to me. But so our goal is to show if we look at the LP norm, that we save square root. And this would prove the main conjecture at the critical case. Now, on the decoupling side of things, tool 1 up here is to work at many scales. So we need to understand how a norm of this type rescales. And in fact, it rescales very beautifully. So it's simple to show that if you know that the pth norm misses our desired exponent by some delta, say, then in fact you can show that for any interval I, you can bound it above by exactly the same power of the length of the interval. What's the point here? Well, if you shift your interval, you actually don't change the LP norm at all because it's an SL2Z change of variables that takes place. Now, over in the efficient congruency world, what does rescaling mean? Well, everything is about integers, so it's a little bit hard to rescale integers quite freely. Instead, what you want to look at is congruence classes. So the equivalent of rescaling on the efficient congruency side is saying that the number of solutions to the Vinogradov system up to size x, with all of them congruent to, say, eta, mod p to the b, is bounded above by the number of solutions without a congruence condition, except in this shortened region, x over p to the b. So this is a result of what's called translation, dilation, invariance if you're used to the integral setting. And it's the exact analog of this rescaling over here. Now what's tool 2? Tool 2, in this case, says that a bilinear estimate controls a linear estimate. Now, linear may not mean exactly what you think, so let me define this. So in our decoupling world, let's suppose that we've chosen some constant capital K, and we're looking at this thing we want to bound, which we'll call, say, A of x for the moment. Now we could rewrite this as a sum of intervals of length x divided by k. So we just partition up our sum of length x into k different pieces. And we could rewrite this as p over 2 times 2 and use that square to get some interactions between different little pieces here. So what would we get? We'd get, after, say, Holder's inequality and some rearrangement, we'd get a factor that depended on the number of pieces, and we'd get an integral over these different neighborhoods of length x over k. And these guys would be to the p over 2 norm. All right, now what did we gain from this? Well, here we have a chance to think a little bit about something like orthogonality. So if we accidentally pick the same neighborhood for both of these, then what we get is you can show by rescaling, we get back this thing we called A, which is the LP norm, except for shorter intervals. Okay? And in fact, if we had picked intervals that were nearest neighbors, you can do a little bit of shuffling around in Cauchy-Schwarz, and you also get back a contribution of this size. So you're left with case 2, which is that I1 and I2 are non-adjacent and distinct. And here, you would assume, for the moment, that you have a bilinear estimate. So the bilinear estimate would be that this is bounded above, say, by some overshoot of what you would desire. If you assume such a bilinear estimate, you can conclude from this argument that the original object you were interested in is bounded above by the same object for a shorter interval, plus this assumed bilinear bound. Okay, it's not yet clear why this is helpful, but let's see in the efficient congruencing world what's going on. It turns out we can bound the Vinogradov mean we're actually interested in by a constant times p times the Vinogradov mean value over a shorter range plus p to the 6 times a bilinear object. What is this bilinear object? This bilinear object counts, it's a max over distinct residue classes, mod p, of solutions to the Vinogradov system where 2 of your variables are congruent. Let me generalize my notation for just one moment. 2 of the variables are congruent to something mod p to the a, and the other 4 are congruent to something else, mod p to the b. And I won't do so now, but you can rewrite this using orthogonality as an integral that looks shockingly similar to this. All right, so I think it's clear there's a very nice analogy between these 2 relationships here. Now, the point I said about many scales also plays a role in both arguments at this point. So what would we do over here? Over here, we took our sum from 0 to x, and we broke it down into smaller pieces of size x over k. What's to prevent us from breaking it down again into pieces of size x over k squared? And indeed, from breaking it down so many times, x over k to the n, that we end up with a length that's, say, less than 100 or something like that. And we can apply a trivial bound to our quantity here. And we end up with solely the bilinear estimate upper bounding this. And in fact, such an inductive argument works very precisely. You have to work carefully with all the constants. But by working at many scales, you show that the bilinear object completely controls the linear object.
Lillian?
Yes?
What is a bilinear object?
This is considered to be a bilinear object. So more generally, if you have an integral, say j equals 1 to m, of some functions, so this would be like a bilinear LP norm, or sorry, M-linear LP norm. And I haven't written out the integral here for reasons of time, but it's bilinear in the same sense. And hence, people call this the linear quantity, even though there's nothing obviously linear about it. Okay, so I want to end with 2 very brief points that I think are some of the most beautiful conclusions you can get out of this. First, I want to show you what it means to work at many scales here. And finally, I'll draw just some pictures to show you what I meant about this 3rd point of transversality of the different components. So what does it mean to work at many scales when you have an estimate of this type? Well, first of all, we passed from counting solutions with no congruence restriction. We passed to counting solutions with a congruence restriction mod p to the a, p to the b, where both a and b were 1. And the key point is it's then possible to pass to congruence restrictions where 4 of the variables are restricted mod p squared, and inductively mod p4, mod p to the 8, and in fact mod p to the 2n for any n you like. And in fact, in the case of the quadratic system, this is not hard to do. There's a complete proof written out in the exposé. So what do we get? For example, the bilinear expression with restrictions mod p is bounded above, it turns out, by some restrictions mod p and some restrictions mod p squared, and then another Vinogradov count in a restricted region. So that's one step of the induction. Inductively, you can show that if you assume that we've missed our desired bound by some delta, then the quantity here that has some restrictions mod p and some restrictions mod p squared is bounded above by our desired bound times the negative power of p. And using induction, you can show this, in fact, for any n. Now, this quickly leads to a contradiction. What can we deduce from this? We can deduce, using various simple relationships like this and our inductive conclusion here, that in fact, the Vinogradov count that we're interested in, and I'm leaving out a term here, so this is only morally speaking, is bounded above by this purported bound times this power of p for any n. Now here we arrive at a problem. Suppose we had defined delta to be the least such number that upper bounds our purported Vinogradov count. Then by taking n to be sufficiently large, we can actually break the definition of delta by showing that delta couldn't have been the least such gain. And so we have to conclude from a relationship of this type that delta must have been 0. And that's actually what we want, because then we will have proved this relationship with no delta at all. Now, why is this working at many scales? Well, you can think of this p-adically as concentrating into smaller and smaller neighborhoods p-adically. This is in duality to the idea that you pass the congruences modulo higher and higher powers of p. We don't have any such p-adic notions on the decoupling side, but there are other notions of inflation versus concentration. And in particular, there's a lemma called the ball inflation lemma, which has ideas of this type built into it. I will end in just a couple moments. I want to give a tiny bit of a flavor of the role of geometry, because it would not be fair to leave the Bourgain, Demeter, Guth world without mentioning this. So I said we want to control a certain bilinear estimate. So what has happened? We had our curve tt squared, and we were looking at points up to x, and we cut it into intervals, say I1 and I2, of length x over k for some constant that I haven't specified. And in doing so, we went from bounding norms of this guy, we became interested in bounding norms restricted to these intervals. And without going into too much detail, in the philosophy of using many scales at the same time, I'm going to suppose that we've also chopped all these intervals one more time to get littler intervals, say of length y, where I won't specify what y is. It's just quite a bit shorter. And it turns out that in order to control integrals of this type, what we need to be able to control are integrals of this type. Okay. Now here we finally get our geometry. What is one of these functions? So in f sub j, this is the sum for t in the interval j of e of t x1 plus t squared x2. Let me rewrite this as a Fourier expansion in fact, this is just a trivial change of notation. So this is the Fourier coefficient. It's either 1 or 0. It's 1 if the first variable is inside the region J, and if the second variable is the square of the first variable, and otherwise it's 0. So this means that on the Fourier side, we have a function whose Fourier coefficients are supported in a box of these proportions. And in particular, we know more about it. We know that they lie on a chunk of the parabola, and that fits inside a parallelogram, call it Qj, of roughly slope you can compute is y plus 2a. What is y and 2a? This is saying that we have an interval starting at the point A of length y. So as this interval gets farther from the origin, the slope gets steeper, and that makes sense. So we have a function whose Fourier support looks like this. It's restricted to a parallelogram with a certain slope. And through notions of harmonic analysis, it means that fj itself is essentially constant on dual parallelograms. So what do I mean by a dual parallelogram? Well, it fits in a dual box. It has the inverse proportions, and it has the orthogonal slope. So it's a parallelogram like that. This is really, really important for the decoupling work. What it means is if you're interested in a very complicated integral like this, it suffices to prove it for functions that you can effectively treat as just being constants on a tiling of the plane by parallelograms of this kind. Now, there are a lot of technicalities, but the main philosophy is like this. So, in fact, to control this bilinear estimate, in the case of k equals 2, the key vision that you need to have is you need to prove that if you take two different intervals, J1 and J2, and you look, let's call this P, Pj, at this parallelogram, then their intersection is bounded above by the product of their two volumes divided by some ball. And I haven't told you what that ball is. Let me just draw this in a picture. So if we start with these two intervals, their Fourier supports are in rectangles with various slopes. And that means the dual parallelograms have orthogonal slopes. Let's say orthogonal to these two slopes. Let's say not orthogonal to each other. So what is this claiming? I want you to think of this as just being barely smaller than 1. And then we can reinterpret this inequality as saying the intersection of these two parallelograms must take up a little bit less than the full volume of either of them. Now, this isn't true for all parallelograms, right? What if we had two parallel parallelograms? We'd be stuck. We could not prove an inequality of this type. The key point about these bilinear estimates is, remember, we only consider the bilinear estimate when we have two of the larger intervals that are non-adjacent, which means that no matter how close J1 tries to get to J2, it's always separated by at least a multiple of x. And what that tells us is that these slopes here are always separated by at least some multiple of the inverse of x. And using very simple trigonometry, you can compute the intersection is indeed strictly smaller than some constant times the volume of either of them. What's the moral of the story? What this philosophy is, it says that tubes that point in different directions have little mutual overlap. This is a non-technical way of stating a very famous conjecture, the Kakeya conjecture, which says that in every dimension n, a Besakovich set must have dimension n. And this is open for dimensions 3 and higher. But one of the key tools of trying to approach the Kakeya conjecture is to prove a multilinear version of it. Sadly, in the Kakeya setting, the multilinear version is known, but it does not imply the original Kakeya conjecture. And the big miracle in this theory of decoupling is that multilinear decoupling completely implies linear decoupling, and multilinear decoupling itself can be proved using multilinear Kakeya, which is known. This is where I'll stop.
Il y a des questions, des commentaires? So in the applications to the Riemann Zeta function, you said for the moment there are no applications. Are there hopes or expectations that this constant dependency should be controlled in a way that allows for such an improvement?
Right, so what I said was a little simplistic. There's another decoupling result of Bourgain, which is from before, a few years ago, which proves a better bound for the zeta function on the critical line, not via the main conjecture, but via decoupling in another setting. And secondarily, there's a better subconvexity estimate by Heath-Brown using the main conjecture. So those are ramifications, but they're not for the zero-free region per se. There's a student of tau, I hear, who is working on explicit computations of the constant, but I don't think anyone's hugely hopeful about the dependence being good enough.
You mentioned the similarities, I mean, the analogy between the two
Yes.
results, efficient concurrencing and decoupling. Was the breakthrough of Wooley, did it provide insight for the Bourgain, Demeter, and Guth?
That's a good question.
Prove that theorem?
So I think I'm just guessing here, I think it made everybody hopeful that this was a good problem to work on. There is an earlier paper of Bourgain and Demeter, which proves a weaker bound for L2 decoupling for the moment curve with an LP norm smaller than this critical exponent. And I think already from there, the applicability was demonstrated, even though their result at that time was much weaker than what was known by efficient congruencing.
Lillian, I understand that for the decoupling technique, the sequence T, the argument could be just one separated. What is the analog of this in the language of congruencing?
So this is a very nice question. So the decoupling, when you actually deduce the result for the Vinogradov system, you don't prove it for equalities. You prove that you're counting the number of solutions to a system of inequalities. And this is much more natural in the harmonic analysis setting, because what you're looking at is, as you're using a weight function who has Fourier support very concentrated near the origin, it does not only pick out things that are zero, i.e. satisfy an identity, it picks out things that satisfy very small inequalities. That's why you're allowed to look at one-separated points. And the decoupling setting, in fact, you're almost forced to think in that generality. In the efficient congruencing world, I guess you'd be looking at things that are p-adically close. Yes. Yeah, I don't think much has been written down about that yet.